Afternoon to some of you, I guess. Welcome to the second day of the conference. So today, just like yesterday, for the talk of yesterday, it'd be good to have the questions at the end. And if you have a question during the talk, you can send them to me either privately or publicly. You can ask them in the chat here, and I'll be looking at the chat during the talk. And so we're gonna have the talk, and at the end we'll have the question time. You can ask questions then, or you can send them to me and I'll ask the questions at the end. So it's my pleasure to introduce Keti Tenenblat from the University of Brasilia, and she's going to talk to us about the mean curvature flow by parallel hypersurfaces.
So thank you. I should thank the organizers for the invitation, and also congratulations for the new research center at the Universidad de la Frontera. So it's a pleasure for me to participate in this inaugural workshop. I will talk on this mean curvature flow by parallel hypersurfaces. And this is a joint work with Yuri dos Reis. Okay, so the outline of the talk is the following. First, I will introduce a mean curvature flow in space forms, and then we will restrict this kind of flow to parallel hypersurfaces, and we will see that such a flow corresponds to isoparametric hypersurfaces. And then we will see that in order to obtain the mean curvature flow for each isoparametric hypersurface, we need to solve an ODE. And then we will find the flow for each isoparametric hypersurface of the space form. And in particular, for each isoparametric hypersurface of the sphere, we will also obtain the collapsing time of this flow, and it will be given explicitly in terms of the dimension, the principal curvatures, and their multiplicity. Okay, so the mean curvature flow is a gradient type flow for the volume functional. Under this flow, a closed hypersurface in the Euclidean space evolves in the direction where the volume element decreases the fastest, and eventually it becomes extinct. Along the flow, singularities may occur, and one is interested in studying such singularities. Now, the uniqueness of the mean curvature flow was already established, and it can be found in these lecture notes on the mean curvature flow by Mantegazza, published in 2011. I should mention that early work on material science already considered this kind of flow. This is in 1920s. And for those who are interested in the mean curvature flow, I suggest a very good survey by Colding, Minicotts, and Pedersen, published in 2015. So the mean curvature flow, you start with an immersion, F, of an n-dimensional manifold into M bar, n plus one dimensional, and you consider it oriented by, you have an n, a unit normal vector field, and then you consider in one parameter family of immersions that I will call F hat of x, t. X is the point in M, and t is, it belongs to an interval in the real line. And you say that this one parameter family of immersions is a solution to the mean curvature flow with initial condition F, if the derivative of F hat with respect to t is equal to H hat times N hat. Here the H hat is the mean curvature of the hypersurface at time t, and N hat is the unit normal vector field at time t. And you want for t equal to 0, F hat to be equal to f of x. So this is the definition of mean curvature flow. And people have studied some special solutions of this flow. For example, self-similar solutions to the mean curvature flow, they are obtained when you consider that they evolve by composing isometries and homotheties. Now, the simplest examples of such solutions are the spheres. The spheres evolve and expand or contract by considering the radius. And eventually the sphere will collapse into a point. And the cylinders, for example, these are examples of self-contracting hypersurfaces, and the cylinders may contract to some lower dimensional Euclidean space. Yeah? So other examples of self-contracting hypersurface in the Euclidean space were given by Angenon in 1992, Klein-Müller more recently, and translation hypersurfaces were studied by all these mathematicians, and these translation hypersurfaces means that the hypersurfaces evolve by a translation in the ambient space. Now, very few examples of the mean curvature flow are known when you consider non-Euclidean space. So in 2000, Hungerbrecht and Schmolzik obtained solutions evolving by the mean curvature flow using isometries of the ambient space. Such kind of flows are called solitons. And they gave a few examples of hypersurfaces in Riemannian manifolds. More recently, in 2009, Liu and Ternk studied the mean curvature flow on isoparametric submanifolds with higher codimension in the Euclidean space and on the sphere. And they proved that the flow preserves the condition of being isoparametric, and they develop insingularities in finite time, converging to a smooth submanifold of lower dimension. So in this joint work with Yuri Dosreis, which was published in Proceedings of AMS, we consider the mean curvature flow on hypersurfaces of space formed by parallel hypersurfaces. And we will see that they can only occur if the hypersurfaces are isoparametric. And we will obtain explicitly the mean curvature flow and the collapsing time when the singularities appear. Now we start with some preliminaries, we fix some notation. So this is the ambient space. I'm considering a space form, curvature K bar. So we are in the Euclidean space, or on the sphere when the curvature is 1, or hyperbolic space when the curvature is -1, sectional curvature. Now the sphere we will consider inside the Euclidean space of dimension n+2, and the hyperbolic space will be considered into Lorentzian space of dimension n+2. So we will consider the initial immersion with the induced metric of the ambient space, and also the immersion to be oriented, and the unit vector field, normal unit vector field. Now, if we consider E1, En to be orthonormal vector fields of principal directions, and K1, Kn the principal curvatures of such an immersion, the mean curvature in this theory of mean curvature flow is considered just to be the sum of the principal curvatures. So no normalizations that sometimes in classical differential geometry is used. But in this theory, people just consider the mean curvature to be the sum of the principal curvatures. So one says that f of m is an isoparametric hypersurface if all the principal curvatures are constant. Now, we are restricting the case to the mean curvature flow in space forms. So we are taking this f hat to be defined in xt and taking values on the space form. And we say that we will have this to be a solution of the mean curvature flow if the with initial condition f, if this derivative is equal to h hat times n hat, at t equal to 0, it has to be f of x. Now here, this x, h hat is exactly the sum of the principal curvatures ki at time t. And this n hat is the normal, unit normal vector field at time t. Now, just going back here, a trivial solution of this equation would be when f is a minimal submanifold, then if you consider f hat of xt to be equal to f of x for each t, so this derivative will be 0, and f has not changed, so it was already minimal, it goes on being minimal. So this is a trivial solution of the mean curvature flow. So you're not interested in getting the trivial solutions. Yeah? Now, as I said, we will restrict ourselves to special solutions of the mean curvature flow by imposing that the flow is given by parallel hypersurfaces to the original immersion F. Just to have a notation which will give us a better, better way to write the results, is we will consider C of Xi to be 1 and S of Xi to be Xi if we are in the Euclidean space. And cosine of Xi and sine of Xi if K bar is 1, which we are in the sphere, and cos of Xi and sinh of Xi if we are in the hyperbolic space. This notation was introduced because if you want to consider parallel hypersurfaces, you have to go at each point of the initial immersion, you have to go along the geodesics tangent to the normal vector field, along the geodesics of the ambient space at a distance Xi, constant distance Xi. So this will be the parallel hypersurfaces. Okay, so when you consider a solution of the mean curvature flow by parallel hypersurfaces, you want to exist a function Xi defined on the interval I, such that Xi of 0 is equal to 0, so that when you evolve, you at t equal to 0, you still have the original immersion. And then f hat t will be the parallel surface at time t. So the parallel depends on the space where you are. If you are in the Euclidean space, this will be just a line. So this is 1, and this is just Xi of t. So you're going along the straight line, along the normal. If you are on the sphere, so this is cosine and sine of Ct. So this is a distance Ct on the sphere. So that's why we are considering everything inside the sphere, which is inside the Euclidean n+2 dimensions. And if you are in the hyperbolic space, this is the geodesic will be cos and sinh. This sum is considered in the Lorentzian space. So at each t, this f hat t is a parallel hypersurface, to f, and the distance is defined by t, yeah, Xi of t actually. So these functions have very simple properties. That the derivative of C respect to Xi is minus K bar times S. S prime of C is exactly C of Xi, and C squared plus K bar S squared is equal to 1. Now, there are simple properties of parallel hypersurfaces that will be very useful for the rest of the talk. And they are very elementary, but we have to point out here that if you are considering a parallel hypersurface in a space form, then the normal at time Xi, at parallel Xi, will be given by minus K bar S times F plus C times N. And the principal curvatures at distance Xi is given in terms of the curvature of the ambient space, those functions S, C, and the principal curvatures of the original immersion. Moreover, if you have E1, En to be an orthonormal basis of principal vector fields, then you can also find out what is the inner product at time Xi of the vectors Ei, Ej. And this will be given by C of Xi minus the principal curvature Ki times S to the square delta Ij. Why is it that, okay. So the first result is the following, that if you consider M as initial data of the mean curvature flow by parallel hypersurfaces, then this will only occur if the initial immersion is an isoparametric hypersurface. And conversely, if you start with an isoparametric hypersurface, you have a solution to the mean curvature flow by parallel hypersurfaces. The proof is simple, but it's very important because the proof gives us the ODE that we need to solve in order to find the mean curvature flow. So I'm assuming that I have already the mean curvature flow by parallel hypersurfaces, and then I take the derivative of f hat. This will give us c prime of t times this expression here. And if you look at what we saw before, so you are imposing that this solution, or you are assuming that this solution is a solution of the mean curvature flow, so that this derivative has to be equal to h hat times n hat. Now this expression here is exactly the n hat at time t. So it turns out that this equality gives you that c prime of t is equal to h hat of t at times x. Now, the left-hand side does not depend on x. So this means that h hat of t does not depend on x, it's constant for each t. So a classical result of Cartan tells you that f of m, actually for each t, the immersion is an isoparametric hypersurface. In particular, the initial one is an isoparametric hypersurface. Now the converse, assume that you have an isoparametric hypersurface and consider c of t to be the unique solution given by this expression. So as we saw before, here c prime of t is equal to the mean curvature. So if we consider that the mean curvature is just the sum of the principal curvature, then you end up finding the right-hand side because it's parallel. We know how to write the principal curvature at time t. Then you have that c prime t should satisfy this differential equation with c of 0 to be 0. So if we start with the unique solution of this ODE, we define f hat of t to be c of ctf plus s of ct times n. And the lemma implies that n hat is equal to this expression, and then you look for the h hat of t, and you find out that this is exactly this expression, which is by construction the c prime of t, and this shows that f hat of t is exactly a solution to the mean curvature flow. And moreover, at time t, you have the function f of c. So I want to mention here that the main step in this proof is that c prime t has to be a solution of this ODE. So this is a consequence of this, of the proof, so that if you start with an isoparametric hypersurface, n being the unit vector, normal vector field, and ki principal curvatures of f, then the solution to the mean curvature flow with initial data f is given by this parallel hypersurface for each t, where c of t is a solution of this ODE, and c of 0 should be 0. Now, so what we have to do in order to find the mean curvature flow by parallel hypersurface is consider all the isoparametric hypersurfaces of space forms. So in the case of the Euclidean space, we know that such a hypersurface is the product of spheres of dimension m times n minus m dimensional Euclidean space. So this will be a cylinder if you have n different from m, and it will be a sphere if m is equal to n, and it will be a hyperplane if m is equal to 0. But the case of hyperplane, you're not interested because it's a minimal hypersurface. In the case of the hyperbolic space, the isoparametric hypersurfaces are given as follows. Either it's an orosphere, and all the curvatures are k equal to, principal curvatures are plus or minus 1, or it's a totally umbilical hypersurface in which this curvature is not equal to plus or minus 1. This is the totally umbilic, which are not the orospheres. Or else you have the hyperbolic cylinders, which is a product of spheres times lower dimensional hyperbolic space. And you have this immersed into the Lorentzian space. Now, the case of the sphere is more complicated. In fact, there is a whole theory that was developed in the last almost 100 years in order to classify the isoparametric hypersurfaces of the sphere. So I will give some of the results here and later we'll give some more, but I should mention that the number of distinct principal curvatures of such a isoparametric surface in the sphere, this number G is restricted to be 1, 2, 3, 4, or 6. Now the classifications for the lower cases, meaning G equal to 1, 2, or 3, is known since the early 1930s, and it was given by Cartan. Now the classification for G equal to 4 started with Abrèche in 1983, and then many authors contributed, and Tang, Fang, Stoltz, Cecile, Xi, Immervoll, and finally, the last results of Xi, which were published in 2011 and 2013, and there's one case which is still not published, but this solved completely the case G equal to 4, and the classifications for G equal to 6 started with Abrèche and was completed by Miyaoka in publications of 2013 and 2016. Okay, so what we have here is the whole panorama of the isoparametric hypersurfaces, where we should try to get those mean curvature flows by parallel hypersurfaces. Okay, so we start with the case of the isoparametric hypersurfaces of the Euclidean space. As I said, these are immersions of product of spheres with Euclidean space. So we have the cylinder or the sphere. And in the case of M different from N, we have the principal curvatures are all equal to K, different from 0. And we have N minus M being null principal curvatures. In this case, the solution of that ODE that we found, it's very, very simple, and one can find it. We are in the Euclidean space, so the parallel hypersurfaces are given by just getting f of x plus the solution C of t of the ODE times n. And from this expression, you find out that the t belongs to an open subset that starts minus infinity up to t star, where t star is equal to 1 over 2mk squared, and at t star, f hat of t will collapse. And it will collapse to a point if m is equal to n, which is mean on case of the sphere, and it will collapse into an n minus m dimensional plane if m is different from n, which is the case of the cylinder. Now, in the case of the isoparametric hypersurfaces of the hyperbolic space, we start with the orospheres. And in this case, all the principal curvatures are k is equal to plus 1 or minus 1. And then you solve the ODE and find that the solution, the C of t, is equal to n times t, where n is the dimension of the immersion. And so you get this to be the parallel hypersurfaces of the mean curvature flow. And for each t, you find out that this is just the orosphere, so it doesn't change. Now, for the case of the totally umbilic hypersurfaces of the hyperbolic space, which are different from the orosphere, then all the principal curvatures will be equal to k, where k cannot be 0. The case of 0 would be the minimal, and you don't want to be orosphere, so you exclude the plus or minus 1. And then you solve the ODE, and you find out that there's this is the expression that you find in order to get the mean curvature flow. And here Q of T is given by this expression. I mean, this term here is a cosh of something, and this is a sinh of something that we obtain by solving the ODE. Now, this Q of T, which appears in this square root, tells you that whenever this goes to 0, then you will have a collapsing point. You know? Now, Q of T is given by 1 minus k squared plus something which is always positive. So the behavior of the mean curvature flow depends on k being less than 1 or bigger than 1 in norm. In the fact, what you see is that if the norm of the principal curvature k is between 0 and 1, then f hat t is defined for all t, and it converges to a totally geodesic n-dimensional manifold when t goes to plus infinity. However, when norm of k is bigger than 1, then f hat of t is defined in this interval where t hat is obtained explicitly just by getting this expression of Q of t equal to 0. And then in this case, it will collapse into a point when t goes to t star. This is what you see when k is between 0 and 1. This is a totally umbilic hypersurface of the mean of the hyperbolic space in the half-plane model, assuming that this curvature is between 0 and 1, and it converges to this totally geodesic hyperbolic space when t goes to infinity. In the case where k is bigger than 1, then you have a geodesic sphere in the hyperbolic space, and it will collapse into a point and you go to infinity. Okay, now let's see the cylinder. The cylinder in the hyperbolic space is given by this immersion of this product. And so you have K1 principal curvatures equal with multiplicity M1, and you have K2 with multiplicity M2, and the product of them should be 1. So we can order them so that K1 is bigger than 1. And so you solve the ODE, the mean curvature flow ODE, and you find out that the flow will be given by this expression, where now cosh of 2 of ct and sinh of 2 of ct is given in terms of a constant a and two functions lt and qt. The constant a is just the sum of the principal curvature, distinct principal curvatures, and the constant b is given in terms of the multiplicities of the principal curvatures, the dimension of the manifold, and this is the difference of the principal curvatures. Q and T, Q of T and L of T are given like that. I observe that these numbers here, they appear naturally when you try to solve the ODE. And I also want to observe that we solve it for 2 times C of T, not for C of T. This comes up just naturally by solving the ODE. So again, the collapsing time will be when Q of T is 0, which is under the square root. And this tells you, because Q of T is this expression, you find out that T star is exactly this term here. And it will collapse into an M2 dimensional focal submanifolds at T star. So you had M1 plus M2 dimensions at the beginning, and you lose M1 dimensions when it collapses. So this is the hyperbolic cylinder. This is the 2-dimensional case into the Poincaré model in the hyperbolic 3 space. In this case, M1 and M2 are equal to 1. You just have one multiplicity for each principal curvature, and it collapses into, in this case, this is a straight line. And this is the focal submanifold of this hyperbolic cylinder through the mean curvature flow. Okay. Now we go to the isoparametric hypersurfaces of the sphere. As I said, this is a more complicated case, and as I mentioned before, the number of distinct principal curvature is G, and this can only be 1, 2, 3, 4, or 6, and this was proved by Münzner in 1980. And Cartan already classified these hypersurfaces when G is less than or equal to 3. And now let's see what happens in each case. When G is equal to 1, we have a sphere. And this sphere is obtained by intersecting the sphere with an hyperplane of the Euclidean n+2 dimension. So this will give you a sphere, which is a isoparametric principal curvature, not one which is totally geodesic, yeah, because the totally geodesic we are not interested in because it's minimal. Now, if G is equal to 2, then the isoparametric hypersurface is a standard product of two spheres, one of dimension L with radius R1, the other one dimension N minus L of dimension R2, where the sum of the squares of the radius is equal to 1. So for G equal to 3, Cartan proved that all the principal curvatures have the same multiplicity M, where M can only be 1, 2, 4, or 8. So this means that the dimension will be always a multiple of 3 times M, and even M is restricted. Now for G equal to 4, Münzner proved that you can order the principal curvatures, K1, K2, K3, K4, such that the corresponding multiplicity, which is M1, M2, M3, and 4, are as follows. M1 can be equal to M3, and M2 equal to M4. And for G equal to 6, Münzner showed that all the principal curvatures must have the same multiplicity M, and Abrech showed that M can only be 1 or 2. So in this case, that you have just 6 or 12, the dimension, yeah? Okay. So now we're actually, in order to obtain the mean curvature flow, we don't need to know specifically how they look like. Actually, they are very complicated, some of them. But we need to know some of the properties of the principal curvatures of the isoparametric surfaces. So up to constant, the principal curvatures are given as follows. For G equal to 1, we just saw it's a sphere, there isn't too much to look at. But when G is equal to 2, 3, 4, or 6, then we have the following. You start with a constant A between -1 and 1, and then you have G fixed already, okay? So A is given, G is fixed, so you can always find S between 0 and pi over G, such that the constant A is equal to this cosine of G times S. And then you can obtain all the mean the principal curvatures, Kj, to be the cotangent of S plus J minus 1 over G times pi, where J is between 1 and G. So if you choose a different A, what happens is that you're choosing a parallel hypersurface to the previous one. Okay, so now because we are on the sphere, the mean curvature flow of an isoparametric hypersurface will be cosine of C of t times sine. This is n, and this is the initial immersion. And what we will see that the function C of t, which gives you the distance in this parallel hypersurface, will be determined by the number G of distinct principal curvature, their multiplicity, and the dimension of the hypersurface. So G equal to 1 is the case of the totally umbilic. All the principal curvatures are equal to K, which is different from 0. And by solving the ODE, you find out the cosh of Xi of t and sinh of Xi of t given by these expressions. Here, Q of t is, so this is defined from -infinity up to t star. And this t star is given from the fact that Q of t star is 0. So in this case, Q of t is given by this expression. So t star is given explicitly in terms of the n and k. And at this t star, f of hat t collapses into a point. So it loses all the n dimensions. Yeah? Okay, the case of G equal to 2, as I said, is the product of two spheres. So you have two different constant principal curvatures, K1, K2. One has dimension L, the other one has dimension n minus L, and the product is -1. And we are assuming that f is not minimal. In this case, you can choose K1 to be bigger than n minus L over L, which is bigger than 1. And the mean curvature flow is given by this expression, where here we have cosine of 2 times of Xt, given explicitly by solving the ODE, and sine of 2 of Xt. There's a constant A here, which is the sum of the two principal curvatures. B is a constant that appears naturally in solving the ODE. And Q of t is this expression here that gives you the collapsing time, given explicitly in terms of the dimension of the n and the principal curvature. So it will collapse into n minus L dimensional focal submanifold at T star. So you lose L dimensions. I'm going to give all the results, actually G3, 4, and 6, and then I will just give you the proof of G equal to 4, which is very illustrative of the way to solve the ODE and obtain the mean curvature flow. So this is the case we just saw, which is a product of spheres into this is the Hopf torus, and the mean curvature flow for this torus in S3, you have L equal to 1, and you lose just L equal to 1, and it collapses into a focal curve, which is this one. Okay, G equal to 3. So in this case, we have 3 distinct principal curvatures. We are not considering minimal case. So we know already that they all have the same multiplicity m, and m can only be 1, 2, 4, or 8. Now, this is a very important step in which you order the principal curvatures. So what I'm doing here is considering K1, K2, K3, so that K1 is bigger than square root of 3 over 3. But by doing this, remember that there is a formula which gives you all the Kj's, right? So by doing this, what I'm doing is considering K1 to be the biggest principal curvature. So you can solve the ODE, but observe that you don't obtain Xi of t, you obtain 3 times Xi of t. And what is 3 in this case? 3 is exactly the number of distinct principal curvatures. So you solve the ODE and obtain cosine of 3 times Xi of t, and those constants appear naturally by this integration. And again, you have a Q of t here, given explicitly like that. And when this goes to 0, you have the collapsing time. And you have a 2m dimensional focal submanifold. And the following, each of these principal curvatures have m multiplicity. What I'm doing by considering this in order, I'm taking the biggest principal curvature to be K1. Now, if K1 is the biggest one, the radius of curvature, which is 1 over K1, is the smallest. So what this is showing you that the collapsing will occur in the smallest radius of curvature. And so by collapsing, you lose this principal curvature and you lose m dimensions. So if you had 3 m dimensions in the original manifold, when you collapse, you get a 2m dimensional submanifold when t goes to t star. G equal to 4. So now you have 4 distinct principal curvatures, and we already saw that we have multiplicity mj, j1, 2, 3, 4. You can order them so that m1, the multiplicity of k1, is the same as the multiplicity of m3. And moreover, k1, I'm choosing here, it will be the biggest principal curvature, which is in this case will be bigger than 1. So the dimension of the manifold is 2 times m1 plus m2. You solve the ODE, and you find out that you obtain actually 4 times C of t, the cosine and sine of 4 times C of t given explicitly. A, again, is the sum of the principal curvatures, and B is a constant given by the multiplicities, dimension, the principal curvature, and Q of t is given like that. So T star, you already know how to do it. You have to take this to be 0, and this will give you the collapsing time. Now observe that what happens to the focal submanifold, where you just lose 1 multiplicity m1. So you started with 2m1 plus 2m2 dimensions, and you end up with the m1 plus 2m2 submanifold. And finally, G equal to 6. You have 6 distinct principal curvatures. They all have the same multiplicity m. So n is equal to 6 times m, but the multiplicity can only be 1 or 2. And now again, we are ordering the principal curvature so that K1 will be the biggest one. In this case, it will be bigger than square root of 3. Kj is given. Once you know the first one, you have the others. And the mean curvature is obtained like that, cosine and sine. You're going along the geodesics of the sphere. And the solution of the ODE is given in terms of 6 times C of t. And all these constants, again, they appear just by solving the ODE. They appear naturally. And the collapsing time is when Q of t goes to 0, and it's given by like that. And it will collapse into a 5 times m dimensional focal submanifold at T star. So these are the results, were all given explicitly. And I would say, okay, so I will give you the proof for G equal to 4 to see what happens, okay? So I'm considering G equal to 4, the mean curvature to be positive. I already ordered the principal curvatures like that. And I know that M1 is equal to M3, M2 equal to M4. And I also know that the mean curvature flow will be given like that, but I have to find C of t by solving the ODE. Now the ODE tells me this, that C prime of t has to be M1 times like kj hat, yeah? M2 kj hat 2, M3 is equal to M1. So I have this term here to be for j equal to 1, 3, and here 2, 4. The multiplicity here is M1 and here is M2. And I also want, so I want to solve this ODE, and C of 0 has to be 0. Well, now I can tell you that a straightforward computation tells you that this right-hand side is equal to n times 4 times sine of 4 of ct plus a cosine of 4 c of t plus b divided by this. Actually, by looking like that, you can never guess that. But we had done the case G equal to 2, G equal to 3. You can imagine when G is equal to 6, which is a little bit messier, but anyway. So by guessing that probably you cannot find xi of t, but you find g times xi of t, we actually show that this term in the right-hand side can be written like that. Now, if you take the you take this 4 times cosine to the left-hand side, and you observe that this cosine, this 4 times sine plus a cosine plus b, the derivative of this is exactly what is on the left side, so you can solve it. You can solve the ODE. And these constants a and b appear naturally when you find out this computation for the sine of 4 times xi and cosine of 4 times xi. So these constants appear just by taking the 4 of xi t, the terms. So you integrate this ODE now, this one, and you integrate and you find that you have 4 times sine of 4 times xi plus a cosine plus b equal to this expression. And then you get rid of the sine, taking the square, and you get to an algebraic equation for cosine of 4 times xi t. And qt is given when you get rid of the sine. It appears naturally here, and this is expression. So you will obtain algebraically what's cosine of
Uh-oh, it looks like her computer froze. Let's wait to see if she can come back in.
Ahí volvió. Keti. O microfone, Keti. O microfone. Ok, agora voltou.
Yeah. Vamos ver aqui, eu vou chutar os números, sei lá, 40, vamos ver se nós estamos aqui. Ok.
Sim.
Exato. Okay, so f hat of t collapses into an m plus. Não, acho que já. Ok.
Mais para frente, estava mostrando a demonstração do caso 4.
Sim. Aqui, okay, yeah. So we found out that the cosine is given by this term. And okay, so T star is given explicitly, and then one can show that the cotangent of 4 times xi of T star is a over 4, and the cotangent of xi of T star is equal to K1. So by showing this, what we are saying that at the collapsing time, we will get to a focal submanifold. Now, I'm saying that when T goes to T star, you lose M1 dimensions, okay? So let's see how you do that. So we had 4 principal curvatures. So I'm choosing here 4 groups of orthonormal frames of principal directions. This for the principal curvature K1, this for K2, K3, and K4. So what one can get, because we know how the inner product evolves with T, one can do the computation of the inner product of EI, EJ for any pair of vectors here. Now, if you choose 2 vectors in this group of principal directions and take T going to T star, this inner product will go to 0 for all this group. If you take any 2 vectors for the other 3 groups, then you find out that the inner product will be 0 if the vectors are distinct, and it will be non-zero for any vector with itself. So this shows that you lost M1 dimensions, and then the rest is okay. So you have M1 plus 2M2 submanifold, the focal submanifold. So what I want to stress here at the end is the main steps for the proofs for any one of those cases, dimension n and g distinct principal curvatures. What you do is you order the principal curvatures so that K1 is bigger than Kj for all j. And the idea here is that you consider the smallest radius of curvature. Then you integrate the ODE for xi of t and obtain g times xi of t, and not xi of t, g times xi of t. And the collapsing time, at the collapsing time, if there is any such t star, the dimension of the focal manifolds will be n minus m1, where m1 is the multiplicity of the principal curvatures k1. So this is the main idea, the steps of the proofs, all of them. And thank you.
Thank you very much. If you want to open your microphones to clap, or you can also clap with virtual hands. Are there any questions? I didn't get any, I didn't see any in the chat, so I don't know if anyone has a question right now. I don't know if that's a question or. Great.
Robert, can I ask a question?
Yes.
Keti, hi. Yeah, it's a small question. It's almost a yes/no question. I am a big fan of sub-Riemannian manifolds, and you know, sub-Riemannian people, they really like the Heisenberg group.
Uh-huh.
And a lot of people have been trying to adapt the mean curvature flow to the Heisenberg group. Okay. Of course, you have some integrability problems associated, right? Because you typically have this non-holonomic distribution. But do you have, for example, this result that that in the sphere you have some very specific amount of G's, right, of different curvature? Do you have something like that in other spaces? For instance, I'm just imagining something of the sub-Riemannian sort, but it's just my professional deformation.
Well, I couldn't tell you if there is any such restrictions for for distinct principal curvatures. I don't know.
But how does it come up?
Okay. So now, there is a theory, for example, that the isoparametric hypersurfaces can be studied in different ways, but one of them, for example, is by considering the isoparametric polynomials. And these, they give you some restrictions, for example, yeah? So, but this is now topologically, or I don't know why they happen, I don't know. But so this is actually the initial way of studying the isoparametric hypersurfaces was by considering level hypersurfaces on the sphere, where there's this F that would give you the level hypersurface, it has to satisfy what is called Cartan-Münzner equations. And then you want the norm, the square of the norm of the gradient of F to be a function of X and G, and the Laplacian of F also has to be a function of G, etc. So I believe that this was the way that people started working on isoparametric hypersurfaces. If there is such a thing for another space, which is not the sphere, I don't know. And as I mentioned before, it took almost 100 years to classify
Okay.
all such.
Yes. All of these. Yes.
Yeah, all of
Yes.
this for the sphere. So, but it's an interesting question. So you should look
Yeah.
for and see if there is something to be done there, or if it can be. I don't know if it can.
Yeah. Okay. Thank you very much.
You're welcome.
Yeah, we will see. Thank you, Keti.
I have a
You're
question. Is there an analogous problem, maybe in the case of complex manifolds?
I don't know. The mean curvature flow it's something that is relatively recent. Let's say started, although I mentioned in the early times of the 20th century, but people started working on this more recently. It's something like the last 20 years or so. So I don't know if this has been done for complex manifolds. I don't know. I have to check in the literature.
Okay, thank you. Are there any other questions? Okay. Well, if not, then let's thank the speaker again.
Thank you.
So we have about 30 minutes, I guess, to the next talk. At 12 o'clock is the next talk. And so you'll probably be put in the waiting room. So you have 30 minutes, I guess, coffee break. You can go to your kitchens and make a coffee. And we'll let you back in, I guess, a few minutes before the next talk. Okay, thank you, Keti.
So bye-bye. It was a